Hi everyone, my name is Karush and I'll be presenting on Deep Hierarchical Reinforcement Learning. I would like to thank the CMTE, RBC and Borealis AI for supporting my research. Chapters 2 and 3 of my thesis serve as prior works at the 34th NeurEps 2020. We'll be going over the problem statement, followed by 3 diverse solutions of evolutionary, energy-based and practical deep hierarchical reinforcement learning. I conclude following a discussion of future work. So let's begin the broad problem of reinforcement learning, which states that reinforcement learning does not extend to practical real-world scenarios. There are various hindrances which provide reinforcement learning and its applications to restrict towards real-world scenarios. These can be broadly grouped into 3 buckets. The first one being scalability, wherein the agent faces large states and action spaces. The second one being fast-paced dynamics arising from the stochasticity in estimates. And the third one being practical viability, wherein the scenario of trial and error just does not extend to real world applications and just does not present any meaningful patterns. My work addresses these 3 problems using a single solution, which is hierarchical learning. So what are hierarchies? Consider a small example wherein a child learns to solve a small task, let's say to sit on a table. Once the child has learned to sit, he can leverage this insights and skills to perform a range of more complex tasks such as work out, play, or ride a bicycle. This composition of sequential tasks is called hierarchy. Hierarchies aid in abstraction of complex behaviors which result in a sequence of problems. Hierarchies allow the agent to learn over variable temporal spans such as the long horizon. Recent work has shown that hierarchies are scalable in the number of tasks and that they demonstrate potential for practical progress. My work aims to leverage hierarchies to solve the aforesaid 3 challenges of scalability, stochasticity, and practical viability. We'll first look at evolutionary reinforcement learning, which tries to address scalability. Agents face a large number of states and action spaces which hinders their performance in the long horizon. Evolutionary methods, on the other hand, demonstrate scalability, but this comes at the cost of hyperparameter sensitivity and sample efficiency. However, a recent combination of the two has shown that this demonstrates suitable performance. But before proposing a problem solution, let's look at the problem and understand what its insights are. Consider a small scale setting, such as the discrete cyclic MDP. The setting has 3 states, wherein the agent is forced to move right continuously. As soon as the agent moves left or stops moving, it faces a negative reward and the episode terminates. What you'll see in this environment's performance from left to right is that evolutionary methods demonstrate improved performance. They demonstrate improved scalability in the number of CPU resources and the number of offsprings. However, these improvements come at the cost of hyperparameter sensitivity, wherein a small change in their parameter values leads to a large change in their performance. So how can we combine these 2 methods to leverage improved performance along with sensitivity? To this end, I introduce the evolution-based soft actor critic, or E.S.A.C. We begin by evaluating a population of winners followed by selecting the winners and mutating them to form the new population. This is the evolutionary phase on the left. On the right, you see that the SSE agent learns from experiences sampled from a replay buffer and optimizing using policy gradients. This is the RL part on the right. The novel component is the automatic mutation tuning, which I'll now discuss in detail. Automatic mutation tuning, or AMT for short, is a tuning mechanism which allows the agent to learn and tune its parameters simultaneously. The method maximizes mutation rate without making use of gradient-based updates. So what you have is a loss-based update signal which updates the mutation rate based on the deviation between the best and the average learner in the population. Practical update of AMT clips the update to reduce noise and stochastic estimates arising from mutations. Provision of the AMT allows E.S.A.C. to scale to high-dimensional task spaces while tuning its parameters on the fly. Upon evaluating E.S.A.C. along with AMT, we see that it demonstrates improved performance on a range of challenging control tasks. It demonstrates improved performance in comparison to state-of-the-art SAC, TD3, and PPO. Note that it also presents scalability to higher dimensional tasks such as humanoid stand, humanoid walk, and humanoid run. We can visualize these behaviors during the agent's interaction in the environment. On the left, you see that agent presents robust behavior by preventing the robot to falling. On the right, you see that the agent presents consistent running gait on the cheetah robot. Similarly, agent extends itself to higher dimensional tasks. Note that the agent controls the 21 degree of freedom humanoid robot on bottom left, which is significantly challenging from a control perspective. A further detailed look into the scalability tells us that E.A.C. demonstrates efficacious use of CPU resources and reduced number of gradient-based updates. It improves hyperparameter sensitivity of the overall method by introducing only one parameter which is tunable. This is the only tunable parameter in an algorithm known as the clip parameter, and it overall reduces the tuning capability and sensitivity of the method. While ESCC scales well to complex tasks, it does not demonstrate improved performance in the case of number of agents. To address this challenge, we look at energy-based reinforcement learning, which tries to address stochasticity. Abrupt dynamics hinder the optimal policies of agents, such as surprising states steer the agent's belief towards suboptimal policies. What you see here is that state-of-the-art multi-agent methods accumulate errors across their training, which are hard to diminish. This can be further studied in the setting of multi-agent value factorization. The setting consists of nonlinear factorization of Q values of all agents in the system. So what you have visually is that a number of agents interact together and yield their individual Q values, which are combined together in the mixer and interact with the nonlinear world. This nonlinear approximation yields stochastic estimates which sufficiently provide stochasticity to the agent's Q value estimates. To address these concerns, I introduced the energy-based mixer, or MX for short. The MX algorithm begins by estimating surprise using an energy-based function across all agents in the system. Upon estimation of surprise, the agent minimizes surprise in the environment by acting along this estimate. Once this minimization takes place, the system then updates its beliefs based on the data collected from the environment. This cycle repeats till the time the system reaches a minimum surprise point or a niche. Bottom right, you see the architecture of the energy-based method, or MX. The method takes an input as state, action, and deviations across a batch and outputs a surprise value. This value, called VA SURP, is operated by the energy operator to yield the final energy-based estimate, which is used in the joint Q-learning algorithm. We can now evaluate MX and observe its performance in the environment. When compared to state-of-the-art multi-agent learning methods, MX demonstrates improved performance on 9 out of 12 scenarios on the StarCraft multi-agent challenge benchmark. It improves collaboration and robustness across surprising states, and it demonstrates stability across its random runs. We can visualize these behaviors of agents during their interaction in the environment. This demonstrates surprise, robust behaviors when agents together collaborate to defeat their enemy teams. I direct your attention to the top right plot, wherein you see the agents collaborate together on a significantly challenging scenario. The agents are presented with a significantly large number of enemies, that is 27 opponents. The only optimal policy here is to collaborate and sacrifice the lives of fellow agents in order to win the game. And what you see is that the agents learn this behavior and become robust to surprising enemies, hence demonstrating improved performance. The MX method presents suitable stochastic robustness. However, it does not demonstrate any insights for practical usage because the setup consists of only simulation and video-based games. So, how do we extend this to practical scenarios? To this, I turn our attention to the pivotal aspect of my work, which is practical deep hierarchical reinforcement learning. We would like to translate surprise robust behaviors to practical settings, and we would like to do this by leveraging a diverse set of hierarchies to solve variable tasks. To do this, we study the structure of the problem, which is the MDP. On top, you see that the MDP can be decomposed into a sequence of sub-MDPs which form a Markov chain. And on bottom, you see that the MDP can be decomposed into a head-to-tail graphical model, wherein the parent node presents the initial MDP and child nodes present the subsequent sub-MDPs. Corresponding to our problem statement, we focus on the top sub-MDP structure since it readily extends to the practical reinforcement learning setting. Keeping this in mind, I introduce you to trade execution using reinforcement learning, or trader for short. Trader is a trading framework which trains a reinforcement learning agent to optimize profits from real market stock data. The setup consists of an agent which optimizes profits using the actor critic framework, making use of policy gradient updates. I make use of the energy-based surprise minimization scheme introduced in the previous section. The hierarchical component of the actor consists of two networks, which is the predictor network and the order network. At each time step, the actor samples a state from the environment, which is a vector of price transitions. The predictor network takes in the state and outputs an order quantity, which is a continuous action in the range of -1 to 1. The order network then takes in this order and the state and outputs an action, which is the final bid, corresponding to one of the three choices of either buy, sell, or hold the order quantity. This allows the agent to learn two tasks at the same time, fixing a quantity and placing a bid, and hence becomes robust using the energy-based scheme. Upon evaluating trader for 35 symbols in 2019 fiscal year at 1 million transitions, we carried out large-scale experiments with high-frequency transitions at 1-minute intervals. These experiments were conducted for multiple runs in COVID-19 market crash and implemented with the PPO algorithm. Trader is suitable for online and offline reinforcement learning with the energy-based surprise minimization scheme, and the large-scale experimentation demonstrates its computational expense. When evaluated on the 35 symbol benchmark, Trader demonstrates improved performance in comparison to standard reinforcement learning agents such as PPO, DD3, and DDPG. On the right, you see that the Trader demonstrates human-like trading patterns. Note that while PPO learns gradually over time that selling more shares is not suitable during a market crash, Trader demonstrates robustness to these surprising price transitions from the beginning and tries to minimize the number of shares sold, hence improving its profitable outcomes in the long horizon. This can be further demonstrated using observing the price or profits obtained for each symbol. On left, you see that the Trader does not demonstrate improved performance on best performing symbols from 2019. This is because the agent's policy has learned the fact that these transitions are risky and there is no point in making a profit on them. On the other hand, Trader demonstrates significantly high profits on worst performing symbols of 2019. This is because the policy has learned to greedily leverage these symbols and accumulate as much profit as possible. A thorough ablation study of Trader and its components presents the various suitability approaches used in this scheme. On left, you see that balance presents a suitable reward learning signal, providing stable learning. On right, you see that Trader requires the energy-based scheme to optimize its long horizon profits. Similarly, on left, you see that as the trading burden for Trader increases, that is, as we increase the seed amount for Trader from $10,000, $20,000 to $50,000, Trader's performance improves drastically, meaning that it has suitably learned to leverage large trading amounts. On the right, you see that the provision of a hold action allows Trader to save its assets and wisely trade in the long horizon, hence accumulating more profits. We can gain more intuition into Trader's performance and human-like patterns by observing the number of shares sold. On left, you see that Trader presents improved performance in comparison to other standard scheme wherein the energy-based minimization is absent. On right, you see that the provision of a hold action makes this performance more consistent across its random runs, indicating that Trader has learned to make long horizon profits. This just goes to show that Trader is more human-like in comparison to other reinforcement learning methods. The provision of a human-like trading agent demonstrates that reinforcement learning does extend to practical real-world problems. We looked at evolutionary reinforcement learning, which provides scalability to large action spaces and provides efficacious use of hardware resources. We looked at energy-based reinforcement learning, which minimizes surprise across all agents and addresses overestimation bias in multi-agent learning. And lastly, we looked at practical hierarchical reinforcement learning, which presents the large-scale success of hierarchical RL and demonstrates an agent which learns human-like trade patterns with profitable outcomes. While my work rigorously explores these areas, it omits certain training strategies which might help steer research towards this direction. Evolutionary RL can be further improved to tackle sparse rewards using meta-controllers and intrinsic motivation frameworks. Energy-based reinforcement learning can tackle increasing stochasticity in safety control and sensitivity analysis settings. Lastly, practical deep hierarchical reinforcement learning can be improved in terms of its data efficiency, and it must tackle non-stationarity of the market environment. On a final note, reinforcement learning is a growing field. While other learning methods such as supervised and unsupervised learning are built on years of research, with the first classification model coming out in 1950, reinforcement learning has only recently gained attention. To this end, I hope that my thesis serves as a stepping stone in this direction, and I hope that this work presents a motivating example for application of reinforcement learning to practical real-world problems. With that, I thank you for your attention, and I welcome any questions or comments from committee members or the audience.